Hello, welcome to Management Science Studio. I am Vahid Lotfi and I am an Emeritus Professor of Management Science. In this video, I will demonstrate how to solve a mixed integer linear programming problem using the Microsoft Excel solver. So let's get started. Let's do an example problem. A company makes two types of products, X1 and X2, using three machines Y1, Y2, and Y3. Product X1 requires 5 hours of processing time on machine Y1, 4 hours of processing on machine Y2, and 1 hour of processing on machine Y3. Product X2 requires 5 hours of processing on machine Y2 and 1 hour of processing on machine Y3. The unit profits for products X1 and X2 are $50 and $70 respectively. The total available hours of machines Y1, Y2, and Y3 are 500, 400, and 120 respectively. And the setup costs for machines Y1, Y2, and Y3 are $1,000, $2,000, and $1,500 respectively. We wish to know how many units of each product X1 and X2 should be produced to maximize the total profit. Now let's look at problem formulation. We are going to use the two decision variables X1 and X2, where X1 will be the number of units of X1 to be produced and X2 will be the number of units of product X2 to be produced. And then we will use the 0, 1 or binary variables Y1, Y2, Y3 to account for the machine Y1, Y2, and Y3 setup. More specifically, we let Y1 equal to 1 if machine 1 is used, 0 otherwise. We let Y2 equal to 1 if machine 2 is used and 0 otherwise, and we let Y3 equal to 1 if machine 3 is used and 0 otherwise. Now we can look at the mixed integer linear programming problem formulation. The objective function will be maximize 50x1 plus 70x2 minus 1000 y1 minus 2000 y2 minus 1500 y3. Notice that if y1 is set up, the value of y1 will be 1 and the setup cost of $1,000 is incurred. Similarly for y2 and y3. Subject to our constraints. For machine 1, we have 5x1 less than or equal to 500 times y1. So if machine 1 is to be used, then y1 has to be 1, which would make the right hand side 500, and it allows for x1 to use the processing time of machine y1. However, if machine y1 is not used, y1 will be 0, the right hand side will be 0, and product x1 cannot use any processing time on machine y1. The second constraint for machine y2, 4x1 plus 5x2 less than or equal to 400 y2, and for machine 3, x1 plus x2 less than or equal to 120 y3. And our non-negativity constraints, the usual for x1 and x2 greater than or equal to 0, and y1, y2, and y3 are 0, 1 variables. I will now use another worksheet to show you how to use the solver to solve this problem. Again, I posted the original problem here, the objective function 50x1, 70x2, minus 1000 y1, minus 2000 y2, minus 1500 y3, subject to our three constraints and the non-negativity constraints, and defining y1, y2, y3 to be the binary variables. Notice that this problem is not in the standard form because the variables y1, y2, y3 appear on the right hand side. So in order to convert it to a standard form, we'll have to take them to the left hand side. So here is the problem restated in the standard form. Same objective function, constraints are 5x1 minus 500y1 less than or equal to 0, 4x1 plus 5x2 minus 400y2 less than or equal to 0, x1 plus x2 minus 120y3 less than or equal to 0, and the non-negativity constraints. I will start defining the variables and the coefficients in this area here, and we are going to go ahead and move forward. We start by entering our decision variables, that is x1, x2, y1, y2, and y3. In this cell I will have the objective value, so let me just put a label here. This will be the objective value. And I'm going to have the used values below here. I'll have the relations in this column and the right hand side in this column. So now I'm ready to label the columns. The first one will be solution. So the solution values will be in 5th row. I make this the same format. Okay. Right below it, I will have the objective function coefficients and the 3 constraints. I'm just going to copy and paste the labels. Now we're ready to enter our coefficients. For solutions, I will temporarily put zeros. The objective function value we will define later. For objective coefficients, we wanted to maximize 50x1, 70x2, minus 1000y1, minus 2000 y2, and minus 1500 y3. Now we go ahead and look at constraint coefficients for machine 1. They were 5, x1, no x2, minus 500 y1, no y2, no y3. The used cell I will define later. The relationship was less than or equal to, and the right hand side was 0. We go to constraint number 2. We had 4x1 plus 5x2, no y1, minus 400 y2, no y3. Right hand, the relationship is less than or equal to, right hand side is 0. And for machine 3, we have 1x1, 1x2, no y1, no y2, and minus 120 y3 less than or equal to 0. Now we have to define our objective function value, which is going to be the product of the objective function coefficient multiplied to the solution value. For this cell, I will use the sum product command. So this cell is going to equal to sum product of the solution values multiplied to the objective function coefficients. The used value of constraint 1 is going to be the sum product of the solution values, which I will make them absolute cells, multiplied to constraint 1 coefficients. Because I made the solution value cell references absolute, I can now copy this formula to the other two rows and they will form the same sort of formula. Here's an example. See, it's multiplication of solution values to the constraint coefficient number 3. We are now ready to go ahead and use the solver command to solve this problem. So we go to the data and then select solver and start defining our values. The value of the objective function is going to be in this cell. We want to maximize. Variables are located in this cell, in these cells, and we are now ready to add our constraints. The first constraint is going to be the used value in this cell, but because all three constraints are the same, I can actually copy them and enter them as one command. Relationship is less than or equal to, and the right hand sides are here. So we just add that constraint, those three constraints. Now we are ready to enter our definition of the three binary values. In this case, we are going to highlight the cells for y1, y2, y3, and instead of a relationship, we are going to select binary. And notice I don't have to define any value, and I'll just click OK. Now I have the problem defined completely in front of me. We leave the non-negativity constraints alone. Those are for x1 and x2 variables. We want to select the LP, simple XLP, and we are ready to solve the problem. So here is the solution. We'll click OK, and we can see that solver solved this mixed integer linear programming problem with solution values of 0 for x1, that is, we do not want to produce the first product, 80 units of product 2 or x2. Machine 1 is not set up. Machine 2 and machine 3 are set up for the total objective function value of 2100 units. And that is how we solve a mixed integer linear programming problem.